What if I told you that most stars in our galaxy are not alone? That the sun we know, solitary and singular, is actually the exception rather than the rule? Out there in the cosmic darkness, countless stellar pairs dance together in orbits that have lasted longer than entire civilizations. They spin and sway to the silent rhythm of gravity, locked in embraces that will endure for billions of years. Tonight, we embark on a journey to witness these cosmic partnerships, to understand the elegant choreography written in the laws of physics, and to discover why the universe seems to prefer companions over solitude. Are you ready to see the stars in a completely new light? Let's begin with a revelation that changes everything we thought we knew about the cosmos. When you look up at the night sky, you see stars scattered like diamonds on velvet. Each point of light seems independent, a solitary beacon in the void. But this perception is an illusion created by distance. If we could journey out among the stars themselves, we would discover something extraordinary. More than half of all stars in our Milky Way galaxy exist not as lonely travelers, but as members of binary systems. Two stars, bound by gravity, orbiting a common center of mass in a dance that began billions of years ago. Think about what this means for a moment. Our sun, which we consider so normal and typical, is actually unusual in its solitude. Out there among the hundreds of billions of stars in our galaxy, the majority have companions. They were born together from the same cosmic cloud, and they will spend their entire lives locked in orbital embrace. Some are separated by distances greater than our entire solar system, taking centuries to complete a single orbit. Others spiral around each other in mere hours, so close that their outer atmospheres nearly touch. This is not a rare phenomenon or an exotic curiosity. This is the normal state of stellar existence. Why does the universe favor these partnerships? What advantage does a binary system have over a solitary star? The answer lies in the very process of star formation itself, in the swirling clouds of gas and dust where stars are born. When a massive cloud begins to collapse under its own gravity, it rarely forms a single, perfectly centered object. Instead, turbulence and rotation within the cloud create multiple centers of condensation. These separate clumps of matter continue to fall inward, but instead of merging, they often begin to orbit each other. The angular momentum of the original cloud is preserved, transformed into the orbital motion of two distinct stars. As you drift through this hour with me, imagine what it would be like to live on a planet orbiting a binary star. You would experience something humans have never witnessed. Two suns in your sky. Depending on the orbital configuration, you might have periods where both suns are visible simultaneously, bathing your world in double daylight. Or you might experience complex patterns of dawn and dusk as one sun sets while the other rises. The night sky on such a world would be profoundly different from ours, with stellar shadows and twilights unlike anything we know. The discovery that binary stars are so common has transformed our understanding of galactic architecture. When early astronomers first turned their telescopes to the heavens, they began to notice that certain stars appeared to be doubles. At first, many assumed these were simply chance alignments, two unrelated stars that happened to lie along the same line of sight from Earth. But careful observation over years and decades revealed the truth. These stars were genuinely bound together, moving through space as a single system, their positions relative to each other changing in predictable patterns as they orbited their mutual center of mass. Now imagine yourself floating in the vast emptiness between stars, watching a binary system from a distance. From this perspective, the dance becomes clear. Two stars, perhaps different in color and size, trace matching curves through the void. They never collide, never escape. The mathematics of their motion are as precise as clockwork, governed by the same gravitational laws that keep planets in orbit around suns. Each star pulls on the other with a force that depends on their masses and the distance between them. This mutual attraction bends their paths into ellipses or circles, a choreography written by Newton and refined by Einstein. As we prepare to explore the different types of binary systems, consider this remarkable fact. Some binary stars are so close together that they complete an orbit in less than a day. Others are so distant from each other that their orbital periods stretch across millennia. Yet all of them follow the same fundamental laws, the same elegant mathematics. In the cosmos, scale may vary wildly, but the underlying principles remain constant. This is part of what makes astronomy so deeply satisfying. The universe operates according to rules we can understand, patterns we can predict, beauty we can appreciate even across the gulf of space and time. You might wonder why we care about binary stars beyond simple curiosity. The answer is profound. Binary systems serve as cosmic laboratories where we can measure fundamental properties of stars that would otherwise remain unknown. By watching how two stars orbit each other, by measuring the period and shape of their orbits, astronomers can calculate their masses with precision. This is something we cannot easily do with solitary stars. Binary systems give us the key to understanding stellar physics, allowing us to test our theories about how stars work, how they evolve, and ultimately, how they die. Let us now descend deeper into the subject and explore the first category of binary stars, those we call visual binaries. These are the systems where both stars can be distinguished as separate points of light through a telescope. They are typically wider systems, with the two stars separated by distances large enough that we can resolve them individually from our vantage point across interstellar space. When you look at a visual binary through a telescope, you see two distinct stars, perhaps of different colors and brightnesses, sitting close together against the background of more distant stars. This is the most direct and intuitive type of binary system. The process of confirming that a visual binary is a true gravitationally bound system requires patience. Astronomers must observe the system repeatedly over months, years, or even decades. With each observation, they carefully measure the position of each star relative to the other. Slowly, as time passes, the orbital motion becomes apparent. The stars trace out their elliptical paths across the sky, moving in relation to each other while maintaining their partnership. This long baseline of observations allows us to determine the true orbital period and shape, revealing the intimate gravitational waltz playing out across the light years. One of the most famous visual binaries is the star system of Sirius. You know Sirius as the brightest star in our night sky, a brilliant beacon that has captivated humanity since ancient times. But Sirius is not alone. It has a companion, a small white dwarf star called Sirius B, orbiting the much brighter Sirius A every 50 years. The companion is tiny and faint, overwhelmed by the glare of its massive partner, but it's there nonetheless. This pairing of a brilliant normal star with a dense stellar remnant tells a story of stellar evolution, of how stars age and transform over billions of years. Another stunning visual binary is Albireo, located in the constellation Cygnus the Swan. When you point a telescope at Albireo, you are rewarded with one of the most beautiful sights in amateur astronomy. Two stars appear side by side, one golden orange and the other sapphire blue. The color contrast is striking, almost artificial in its perfection. These two stars orbit each other over a period that may span thousands of years. They are separated by such a vast distance that their gravitational influence on each other is gentle and slow. Yet they remain bound, two different stellar populations sharing the same small region of space. Visual binaries teach us about the diversity of stellar partnerships. Some consist of stars that are nearly identical, twins born from the same cloud with similar masses and properties. Others are wildly mismatched, with one star vastly outweighing and outshining its companion. The orbital periods range from decades to millennia. The distances between the stars can span from just a few times the Earth-Sun distance to separations measured in thousands of astronomical units. Each system is unique, yet all follow the same physical laws. This combination of diversity and underlying unity is part of what makes these systems so compelling to study. When we measure the orbits of visual binaries carefully over long periods, we gain access to one of the most fundamental properties of stars. We can determine their masses. The period of the orbit and the size of the orbit are directly related to the combined mass of the two stars through Kepler's laws of planetary motion, refined by Newton's law of gravitation. By timing how long it takes the stars to complete one full orbit and measuring the size of that orbit, we can calculate how much mass must be present to produce the observed motion. This is information we simply cannot get from observing a single isolated star. Let your mind drift now and imagine standing on a world that orbits one member of a visual binary system. Your home star is the one you orbit closely, the one that provides your warmth and light. But out there in your sky, visible both day and night, is the companion star. It appears as an exceptionally bright point of light, far brighter than any planet, yet not quite close enough to cast significant heat or light on your world. Over the course of years or decades, you would watch this companion star move slowly across the constellations, tracing its orbital path. Ancient astronomers on such a world would have noticed this motion, developing theories of cosmic mechanics, perhaps different from our own. Visual binaries remind us that the cosmos operates on timescales both vast and measurable. Some of these systems have been observed for well over a century now, with astronomers carefully documenting their orbital motion across multiple generations. These long-term studies represent a continuity of human curiosity and dedication, a chain of observation linking the past to the present. When modern astronomers examine a visual binary, they often consult records made by observers long dead, adding new data points to orbits that will continue to be tracked by astronomers not yet born. In this way, the study of binary stars connects us across time. Now, we turn to a more subtle type of binary system, one that reveals itself not through separation we can see, but through the physics of light itself. These are the spectroscopic binaries, systems where the two stars are too close together or too far away for us to resolve them as separate points of light. When we look at a spectroscopic binary through a telescope, we see only a single point of light. Yet hidden within that light is evidence of two stars orbiting each other in a cosmic dance we can detect through careful analysis of their spectrum. This is astronomy at its most elegant, using the properties of light to reveal what our eyes alone cannot see. The key to detecting spectroscopic binaries lies in the Doppler effect, the same phenomenon that causes the pitch of a siren to change as it moves past you. When a star moves toward us, the wavelengths of its light are compressed slightly, shifting toward the blue end of the spectrum. When it moves away, the wavelengths stretch out, shifting toward the red. In a binary system, one star is always moving toward us while the other moves away, then they reverse as they orbit. By measuring these periodic shifts in the spectral lines of the starlight, we can detect the presence of two stars and measure their orbital velocities even when we cannot see them as separate objects. Some spectroscopic binaries are single-line systems, where we can detect the spectral lines of only one star. This happens when one star is much brighter than its companion, drowning out the fainter star's light. We observe the spectral lines of the bright star shifting back and forth rhythmically, moving from blue to red and back again with a period that might be days, weeks, or months. Even though we see evidence of only one star directly, the periodic nature of the shift tells us something massive and invisible is tugging on it, pulling it into orbital motion. The dark companion reveals itself through its gravitational influence alone. Other spectroscopic binaries are double-lined systems, where both stars contribute enough light for us to see their individual spectral signatures. In these systems, we observe two sets of spectral lines, both shifting in opposite directions as the stars orbit. When one set of lines moves toward the blue, the other moves toward the red, and vice versa. The two sets of lines swing back and forth like partners in a dance, perfectly synchronized in opposite motions. From these measurements, we can determine not just that two stars are present, but also their orbital velocities, their masses, and the orientation of their orbit relative to our line of sight. Many spectroscopic binaries have very short orbital periods, completing their dance in just days or even hours. This tells us that the stars must be quite close together, perhaps separated by only a few stellar diameters. At such close range, the gravitational forces between them are intense. The stars may be distorted from perfect spheres, stretched toward each other by tidal forces. Their atmospheres might even extend outward to meet, creating a region where the gases of both stars mingle. These close encounters create conditions that simply don't exist around solitary stars, exotic environments where stellar physics takes on new and fascinating forms. Consider the patience required to study these systems. Astronomers must obtain spectra repeatedly over weeks, months, or years, capturing the stars at different points in their orbits. Each spectrum requires careful calibration and analysis, measuring the precise wavelengths of numerous absorption lines to detect shifts that might be just a tiny fraction of a nanometer. Only by compiling many such measurements can the orbital motion be reconstructed. It's detective work of the highest order, piecing together the motion of unseen objects from subtle clues in starlight that has traveled across interstellar distances to reach our instruments. Spectroscopic binaries have taught us that stellar companionship is even more common than visual binaries alone would suggest. Many stars that appear single to the eye are actually binary systems revealed only through spectroscopy. When we combine our knowledge of visual binaries with the detection of spectroscopic binaries, we arrive at the realization that the majority of stars in the galaxy have companions. The universe appears to have a preference for pairing, for creating gravitationally bound systems rather than isolated objects. This has profound implications for star formation theory and for the prevalence of planetary systems, which must form in these more complex gravitational environments. As you continue to relax into this journey through the cosmos, let the rhythmic nature of these orbital motions calm your mind. Picture the spectral lines swinging back and forth, blue to red, red to blue, in perfect periodic motion. Imagine the two stars themselves, locked in their eternal orbit, their motion as regular as a heartbeat or the ticking of a cosmic clock. There is something deeply soothing about this predictability, this demonstration that even in the vast and sometimes chaotic universe, there are patterns and rhythms we can understand and rely upon. The dance continues, as it has for millions of years, as it will for millions more. There exists a special category of binary star system that offers us a unique window into stellar properties, one where chance alignment combines with orbital mechanics to create a phenomenon we can observe with remarkable precision. These are the eclipsing binaries, systems where the orbital plane is oriented edge-on as seen from Earth. As the stars orbit each other, they periodically pass in front of one another from our perspective. When this happens, we observe a temporary dimming of the system's total light output. One star eclipses the other, creating a predictable pattern of brightness, variations that repeats with clockwork regularity. The light curve of an eclipsing binary tells a detailed story. When we plot the system's brightness over time, we see a pattern of regular dips. The primary eclipse occurs when the larger or brighter star is blocked by its companion, causing the most dramatic drop in light. The secondary eclipse happens when the smaller or fainter star passes behind its partner, causing a shallower dip. By analyzing the shape, depth, and duration of these eclipses, astronomers can determine the sizes of both stars, their temperatures, their orbital velocities, and even the angle at which we're viewing their orbital plane. It's a wealth of information encoded in simple variations of brightness. Perhaps the most famous eclipsing binary is Algol, whose name comes from the Arabic phrase meaning the demon star. Ancient astronomers noticed that Algol seemed to vary in brightness in a strange and periodic way, dimming noticeably every few days before returning to its normal brilliance. For centuries, this behavior was mysterious and somewhat unsettling. It wasn't until modern times that we understood what was happening. Algol is actually a binary system where a large but relatively dim star periodically passes in front of a smaller but much brighter star. When the eclipse occurs, Algol's apparent brightness drops by more than half for several hours before the eclipse ends. Eclipsing binaries serve as cosmic laboratories for testing our theories of stellar structure and evolution. Because we can measure both stars' sizes and masses with high precision, we can compare these measurements against theoretical models of how stars should behave. Do stars of a given mass and temperature have the sizes our models predict? Are their surface properties consistent with our understanding of stellar physics? Eclipsing binaries provide some of the most rigorous tests of these theories. When observations and theory agree, it strengthens our confidence. When they disagree, it points us toward new physics we haven't yet understood. Some eclipsing binaries display additional complexity that makes them even more interesting. If one or both stars are rotating rapidly, they may be slightly flattened at their poles, like a ball that has been compressed from top and bottom. This means that during an eclipse, we might see different amounts of light blocked depending on which part of the star is passing in front of the other. The system's brightness variation becomes more complex, with subtle features in the light curve that reveal the shape of the stars themselves. Even the dark spots on stellar surfaces, analogous to sunspots, can be detected through careful analysis of how they affect the eclipses. The regularity of eclipsing binaries makes them useful as cosmic timekeepers. Astronomers have monitored some of these systems for over a century, timing the eclipses with ever-increasing precision. In most cases, the eclipses occur exactly when predicted, demonstrating the clockwork nature of orbital mechanics. But occasionally, astronomers detect tiny deviations from the expected timing. These deviations can reveal the presence of additional objects in the system, such as planets or even third stars, whose gravitational influence subtly affects the binary orbit. Thus, eclipsing binaries can serve as signposts pointing toward hidden companions we might not detect any other way. Let your thoughts drift to what it might be like to observe an eclipsing binary from up close, from a vantage point somewhere in the system, but far from both stars. You would witness a spectacle that no human has ever seen. As the orbital dance brings one star in front of the other, you would watch a partial or total stellar eclipse unfold. The light flooding your location would dim dramatically as one star's disk covers the other. If the eclipse is total, you might see the corona of the background star extending beyond the eclipsing star's edge, creating a ring of light. Then, gradually, the stars would separate and full brightness would return, only to repeat the show hours or days later. The predictability of eclipsing binaries offers us a sense of cosmic order and stability. In a universe that can seem chaotic and random, these systems demonstrate that gravity creates reliable, repeating patterns. The same eclipse that occurs today will occur again tomorrow, and the day after, and thousands of years from now, with metronomic precision. There's something comforting in this reliability, in knowing that some things in the cosmos operate like perfect machines. As we move forward in our journey, carry with you this sense of celestial clockwork, the knowledge that the universe, for all its vastness, operates according to comprehensible and elegant laws. As we venture deeper into the realm of binary stars, we encounter systems where the stars orbit so close to each other that their mutual gravitational influence becomes not just important, but dominant. In these close binary systems, something remarkable happens. Each star exists within an invisible boundary called its Roche lobe, a teardrop-shaped region of space where that star's gravity is the strongest influence. Material inside a star's Roche lobe is gravitationally bound to that star. But if material crosses the boundary into the other star's Roche lobe, it switches allegiance. This concept of Roche lobes governs the behavior of close binaries and leads to some of the most dramatic phenomena in stellar astronomy. In many close binary systems, the stars are well within their Roche lobes and no unusual interactions occur. But consider what happens as stars age and evolve. As a star exhausts its core hydrogen fuel, it begins to expand, swelling up to become a red giant. If this happens in a close binary, the expanding star may grow large enough that its outer layers reach and then exceed its Roche lobe. When this occurs, material from the outer envelope of the expanding star begins to spill over into the Roche lobe of its companion. Mass transfer has begun, and the binary system enters a new and dynamic phase of evolution, one impossible for isolated stars. The material that crosses from one star to the other doesn't fall straight down onto the companion. Because the entire system is rotating, the transferred material carries angular momentum. As it falls toward the companion star, this angular momentum causes it to spiral inward rather than plunging directly to the surface. The result is the formation of an accretion disk, a swirling disk of hot gas that gradually settles onto the receiving star. These accretion disks can become extremely hot, glowing with X-rays and ultraviolet light. They are sites of tremendous energy release, where gravitational potential energy is converted into radiation as the material spirals inward toward its new home. Mass transfer fundamentally alters the evolution of both stars in the binary. The donor star loses mass, which can slow or even halt its expansion, keeping it from evolving along the path it would have followed in isolation. The receiving star gains mass, which can rejuvenate it, adding fresh fuel to its nuclear fires. In extreme cases, a star that should have died long ago can appear young and active because it has been fed by mass transfer from its companion. The evolutionary timescales of the two stars become coupled and synchronized in complex ways, creating stellar partnerships where each star's fate is inextricably tied to the other. Some of the most energetic phenomena in the universe are powered by mass transfer in close binaries. When the receiving star is a white dwarf, a compact stellar remnant with intense gravity, the accreted material can pile up on its surface until conditions become right for a thermonuclear explosion. This explosion is called a nova, and it causes the system to suddenly brighten by thousands or even millions of times. The nova doesn't destroy the system. Instead, the explosion blows away the accumulated material and the process can begin again. Some novae are recurrent, exploding repeatedly over decades or centuries as mass transfer continues and fresh fuel builds up on the white dwarf's surface. In the most extreme cases, if a white dwarf accretes enough mass from its companion, it can approach a critical threshold called the Chandrasekhar limit. When a white dwarf reaches this mass, about 1.4 times the mass of our Sun, it can no longer support itself against gravity. The star collapses catastrophically, triggering a runaway thermonuclear explosion that completely destroys the white dwarf. This is a Type Ia supernova, one of the most powerful explosions in the universe. These supernovae are so bright, they can outshine entire galaxies for a brief time, and they play a crucial role in enriching the cosmos with heavy elements forged in the explosion. Not all mass transfer is stable and gentle. In some systems, the process can become unstable, with the donor star losing mass faster than the companion can accrete it. The excess material forms a thick envelope around both stars, and the stars begin to spiral closer together, orbiting within a shared atmosphere. This is called a common envelope phase, and it's a chaotic, short-lived stage of binary evolution. The friction of moving through the dense envelope causes the stars to lose angular momentum and spiral inward rapidly. Eventually, either the envelope is ejected completely, leaving behind a very close binary of stellar cores, or the stars merge entirely, combining into a single object. As you continue to relax, let these images of cosmic interaction wash over you. Picture the invisible Roche lobes, the boundaries that govern stellar allegiance. Imagine the streams of gas flowing from one star to another, glowing as they spiral inward through accretion disks. These close encounters between stars are not violent in the way we might imagine violence. They unfold over thousands or millions of years, following the inevitable logic of gravity and stellar evolution. Yet they produce some of the most spectacular sights in astronomy, demonstrations of how matter and energy behave under extreme conditions found nowhere on Earth. The universe is a place of constant transformation, where even stars are not permanent, but continuously change and interact. We now arrive at the most intimate type of stellar partnership imaginable. These are the contact binaries, systems where the two stars are not merely close, but actually touching. Their outer atmospheres are in contact, sharing a common envelope of gas that surrounds both stellar cores. In some cases, the stars are so deeply embedded in this shared envelope that they appear almost as a single peanut-shaped object rather than two distinct spheres. These systems represent the extreme end of stellar proximity, where the boundary between individual identity and merged existence becomes blurred. They are stellar embraces that have lasted for millions of years. How do contact binaries form? One pathway involves a close binary system where both stars have evolved to fill their Roche lobes simultaneously. When both stars expand to the point where their outer layers meet, they begin to share material back and forth. The system settles into a stable configuration where both stars exist within a common envelope. Another pathway involves the aftermath of a common envelope phase, where two stellar cores emerge from the envelope already in contact. Regardless of their origin, contact binaries represent a state of stellar evolution that is unique to binary systems. Isolated stars simply cannot achieve this configuration because there's no second star to make contact with. The orbital periods of contact binaries are typically very short, measured in hours rather than days or years. The stars are so close together that they can complete an orbit in less time than it takes Earth to rotate once on its axis. This rapid rotation means that the entire system is spinning quickly, with the shared envelope rotating as a single unit. Material near the surface of this envelope experiences extreme conditions, whipped around at tremendous speeds by the rotation while simultaneously being pulled inward by the gravity of both cores. It's an environment of constant motion and high energy, even though, to our eyes from far away, the system appears as a stable if variable point of light. Many contact binaries are also eclipsing systems, showing continuous variations in brightness as the two cores orbit within the shared envelope. When we observe these systems, we see a characteristic light curve with two dips per orbital cycle, corresponding to the times when each core passes in front of the other from our perspective. But unlike separated eclipsing binaries, contact binaries also show significant brightness variations between eclipses because the shared envelope is not uniformly bright. Different parts of the envelope have different temperatures and densities, creating a complex pattern of light variation that encodes information about the structure and dynamics of the system. One fascinating question about contact binaries is whether they represent a stable end state or a temporary phase on the way to something else. Some astronomers believe that contact binaries may eventually merge completely, with the two cores spiraling together until they combine into a single, more massive star. This merger would be a dramatic event, releasing enormous amounts of energy and possibly creating an outburst visible across interstellar distances. Other researchers think some contact binaries may be stable for long periods, maintaining their dual core structure within the shared envelope indefinitely. The truth may be that both outcomes occur, depending on the specific masses and properties of the stars involved. The most famous example of a contact binary is W Ursae Majoris, the prototype star that gives its name to an entire class of similar systems. When astronomers first observed W Ursae Majoris in detail, they were puzzled by its behavior. Its brightness varied continuously with a period of just 8 hours, and the light curve had an unusual shape that didn't match any known type of variable star. It wasn't until the concept of contact binaries was developed that the observations made sense. We now know of thousands of W Ursae Majoris type systems throughout our galaxy, making them a common, if extreme, type of stellar partnership. Imagine what it would be like to observe a contact binary from a safe distance nearby. You would see not two separate suns, but a single elongated object, bulging at 2 points where the stellar cores reside. The system would be rotating rapidly, completing a full spin in just hours. You might observe active regions on the surface, areas where magnetic fields break through and create hotspots or prominences of gas arcing above the surface. The entire object would be constantly changing, with convection currents in the shared envelope creating patterns that shift and evolve. It would be unlike anything we observe in our own solar system, a testament to the diversity of stellar configurations the universe can create. Contact binaries push the concept of stellar individuality to its limit. Are these two stars sharing an atmosphere, or is it one object with two cores? The question may not have a definitive answer. In a sense, contact binaries exist in a state between being binary and being singular. They remind us that nature doesn't always fit neatly into the categories we create. The universe is continuous and creative, producing phenomena that challenge our definitions and expand our understanding. As we move forward, keep in mind this lesson. The cosmos is not bound by our expectations. It will always find ways to surprise us, to be more complex and more wonderful than we imagined. The life story of a star is one of the great narratives in astrophysics, a tale of birth, maturity, old age, and death spanning billions of years. For isolated stars, this story follows a relatively straightforward path, determined primarily by the star's initial mass. But for stars in binary systems, the story becomes far more complex and interesting. The presence of a companion introduces new possibilities and pathways, interactions that can accelerate, delay, or completely redirect the evolutionary trajectory of one or both stars. In this segment, let us explore how stellar evolution unfolds when stars are not alone, but part of a gravitationally bound partnership. Consider a binary system where both stars are initially similar, both main sequence stars fusing hydrogen in their cores. If they are widely separated, they will evolve almost as if they were isolated, each following its own path according to its mass. The more massive star will evolve faster, exhausting its hydrogen fuel first and beginning to expand into a red giant. If the stars are distant enough, this expansion causes no interaction. The red giant simply grows larger while its companion continues fusing hydrogen peacefully. Eventually, the red giant will shed its outer layers and become a white dwarf, leaving its companion to continue its own slower evolutionary journey. But if the stars are closer together, their evolution becomes entangled. When the more massive star expands to become a red giant, its outer layers may reach its Roche lobe and begin to overflow onto the companion. This mass transfer rejuvenates the companion star, adding fresh hydrogen fuel to its outer layers. The companion may become more massive than the primary star was initially, and it will shine more brightly. Meanwhile, the donor star loses its extended envelope and is left as a smaller, hotter core. The system has been transformed. What began as a pair of similar stars has become a mismatched duo, one compact and evolved, the other bloated with newly acquired mass. After the primary star has transferred most of its envelope and become a white dwarf, the secondary star continues to evolve. Eventually, it too will exhaust its core hydrogen and begin to expand. When this happens, the roles reverse. Now, the secondary star fills its Roche lobe and begins transferring mass back onto the white dwarf. But accretion onto a white dwarf is a very different process than accretion onto a normal star. The white dwarf's intense gravity compresses the infalling material, heating it to extreme temperatures. The result is a brilliant X-ray source, visible across interstellar distances as a beacon of high-energy radiation. The system has entered a new phase of existence as an interacting X-ray binary. In systems with even more massive stars, the evolutionary endgame can be spectacular. When a massive star in a binary system runs through its nuclear fuel, it explodes as a supernova, either destroying itself completely or leaving behind a neutron star or black hole. If the supernova explosion is asymmetric, it can impart a kick to the remnant, possibly disrupting the binary or at least altering the orbit dramatically. If the binary survives, the system now consists of a stellar remnant paired with a normal star. When the normal star later evolves and expands, it can transfer mass onto the neutron star or black hole, creating some of the most energetic phenomena in the universe. When material from a companion star falls onto a neutron star, the gravitational energy released is staggering. The infalling material is accelerated to a significant fraction of the speed of light before it crashes onto the neutron star's surface. The impact releases more energy per gram than any other process except matter. Antimatter. Annihilation. This energy emerges primarily as X-rays and gamma rays, making these systems among the brightest X-ray sources in the sky. Some of these systems also produce jets of material shot out at nearly the speed of light along the magnetic poles of the neutron star, creating cosmic lighthouses that can be detected across the galaxy. The most extreme binary systems contain black holes, regions of space-time where gravity is so intense that not even light can escape. When a companion star feeds a black hole, the accretion disk becomes a furnace of unimaginable intensity. Just outside the event horizon, the material orbits at nearly the speed of light, heated to billions of degrees by friction and compression. Before it vanishes forever into the black hole, this material radiates powerfully across the spectrum, particularly in X-rays. These systems are among the brightest objects in X-rays, allowing us to study black holes indirectly through their effect on nearby matter, even though we cannot see the black holes themselves. As you absorb these stories of stellar evolution in binary systems, recognize that you are learning about some of the most energetic and dramatic processes in the universe. From the gentle mass transfer between main sequence stars to the violent accretion onto neutron stars and black holes, binary systems showcase the full range of stellar behavior. They demonstrate how interactions between objects can drive evolution in unexpected directions, how complexity emerges from the interplay of gravity and nuclear physics. The universe would be a much simpler and less interesting place if all stars were isolated. It is the partnerships, the interactions, the dances that create the rich tapestry of phenomena we observe when we study the cosmos. Throughout human history, certain stars have captured our attention and imagination more than others. Many of these famous stars, the ones that have been observed and named since ancient times, turn out to be binary systems when examined with modern instruments. In this segment, let us take a tour of some of the most celebrated binary stars in our night sky, cosmic neighbors that have helped us understand the principles of stellar physics and the prevalence of binary systems. These are not distant abstractions, but real systems. You can observe yourself points of light that reveal their secrets when studied with patience and care. We've already mentioned Sirius, the brightest star in our night sky and a jewel of winter skies in the northern hemisphere. Sirius consists of Sirius A, a brilliant blue-white main sequence star more than twice as massive as our Sun, and Sirius B, a white dwarf companion. The two stars orbit each other every 50 years. Sirius B was actually the first white dwarf ever discovered, identified in observations from the late 19th century. The white dwarf is tiny, about the size of Earth. yet it contains almost the entire mass of our Sun compressed into that small volume. Observing Sirius B is challenging because it is lost in the glare of Sirius A, but with good instruments and conditions, it can be seen as a faint pinpoint near its brilliant companion. Another stunning visual binary is Albireo, the head star of Cygnus the Swan. When you observe Albireo through even a small telescope, you are treated to one of the sky's most beautiful sights. Two stars appear side by side, one distinctly golden orange, the other sapphire blue. The color contrast is so perfect it almost seems artificial. These two stars orbit each other over a period estimated to be thousands of years. They are separated by a distance of about 34 billion kilometers, roughly 10 times farther than Pluto is from our Sun. Despite this vast separation, they remain gravitationally bound, locked in their slow waltz for eons to come. For those interested in eclipsing binaries, Algol in the constellation Perseus remains the classic example. Algol's variability was known to ancient observers, though they could not explain it. We now understand that Algol is a triple star system, with the main pair being an eclipsing binary. The primary star is a blue-white main sequence star. Its companion is actually more massive but less luminous, a subgiant star that is transferring mass to the primary. Every 2.8 days, the dimmer companion passes in front of the brighter primary, causing Algol's brightness to drop noticeably for several hours. You can observe this with your own eyes, timing the eclipses and confirming the clockwork nature of the system. One of the closest binary systems to Earth is Alpha Centauri, our nearest stellar neighbor beyond the Sun. Alpha Centauri appears to the naked eye as a single bright star in southern skies, but it's actually a triple system. Alpha Centauri. A and B are a binary pair, two sun-like stars orbiting each other every 80 years. They are separated by distances comparable to the spacing of planets in our solar system. Orbiting much farther out is Proxima Centauri, a small red dwarf that holds the distinction of being the single closest star to our Sun. The Alpha Centauri system is so close that it has been a frequent target of speculation about interstellar exploration and the possibility of planets in the habitable zones of these stars. For those who want to observe a spectroscopic binary, Mizar in the handle of the Big Dipper is an excellent choice. To the naked eye, Mizar appears as a single star, and if your eyesight is good, you might notice its faint companion Alcor nearby. But Mizar is actually much more complex than it appears. When examined spectroscopically, Mizar reveals itself to be a binary system, with each component of Mizar itself being a binary. So what looks like one star is actually four stars in two pairs, all orbiting their common center of mass. Alcor, long thought to be just an optical companion, is now known to be physically associated with the Mizar system, making this one of the most complex nearby multiple star systems we can easily observe. Not all famous binaries are visible to the naked eye. Cygnus X1 is invisible in optical light but blazes brilliantly in X-rays. It was one of the first strong candidates for a black hole, and decades of observation have confirmed its nature. The system consists of a blue supergiant star and a compact object about 15 times the mass of the Sun, far too massive to be a neutron star. The only possibility is a black hole. Material from the supergiant flows toward the black hole, forming an intensely hot accretion disk that emits the X-rays we detect. Cygnus X1 gave humanity its first good evidence that black holes are real objects in the universe, not just mathematical curiosities predicted by Einstein's theory of relativity. These famous binary systems are more than just objects of scientific study. They are our cosmic neighbors, part of the celestial landscape we inhabit. When you look up at Sirius on a winter night, you are seeing light that left that binary system just 8.6 years ago. When you observe Albireo, you are witnessing photons that began their journey decades ago, traveling across light years to reach your eye. These systems connect us to the broader universe, reminding us that we exist within a galaxy full of stellar partnerships, each with its own story, its own evolution, its own beauty. They are invitations to look deeper, to understand more fully, to appreciate the richness of the cosmos we call home. As we continue our journey through the realm of binary stars, an important question arises. Can planets exist in binary star systems? For many years, astronomers were uncertain. The gravitational complexity of two stars orbiting each other seemed like it might prevent stable planetary orbits from forming or persisting. But observations have revealed a surprising answer. Not only can planets exist in binary systems, but they are actually quite common. We've discovered many such planets, worlds that experience the light of two suns, demonstrating that planetary systems are robust enough to form and survive in these more complex gravitational environments. Planets in binary systems can exist in two main configurations. The first is called a circumbinary orbit, where the planet orbits both stars, circling the binary system at a distance greater than the separation between the two stars. From the surface of such a planet, both stars would appear in the sky, and you would witness double sunrises and sunsets. The planet's orbit encircles both stars, and the combined gravity of the binary pair acts like the gravity of a single, more massive star. These orbits can be stable for billions of years, allowing plenty of time for life to potentially develop if conditions are suitable. The second configuration is called a circumstellar orbit, where the planet orbits just one star of the binary pair, staying close enough to that star that the influence of the distant companion is minor. From such a planet, you would have one primary sun providing most of your light and heat, while the companion star would appear as an exceptionally bright point of light in the sky, much brighter than any planet but not close enough to be a second sun. These configurations are stable as long as the planet stays well within the sphere of influence of its host star, not venturing too close to the region where the two stars' gravitational pulls become comparable. One of the most famous circumbinary planets is Kepler 16b, nicknamed Tatooine after the fictional desert planet from Star Wars. Kepler 16b orbits two stars, one about 2/3 the mass of our Sun and the other about 1/5 solar mass. The planet itself is roughly the size and mass of Saturn, a gas giant unsuitable for life as we know it. But its discovery proved that circumbinary planets can exist and can be detected. Imagine standing on a moon orbiting Kepler 16b, watching two suns rise and set in complex patterns, the light and shadows constantly shifting as the orbital dance unfolds. The formation of planets in binary systems presents interesting challenges and questions. Planets form from protoplanetary disks, vast disks of dust and gas that surround young stars. In a binary system, the gravitational influence of two stars can disrupt and truncate these disks, potentially limiting the amount of material available to form planets. Yet we observe that planets do form, suggesting that the process is more resilient than we might have expected. Some binary systems may have circumbinary disks that encircle both stars, allowing circumbinary planets to form. Others may have separate disks around each star, allowing circumstellar planets to develop independently around each component of the binary. The discovery of planets in binary systems has implications for the search for life beyond Earth. For many years, scientists worried that the complex dynamics of binary systems might make them poor candidates for habitable planets. But we now know that stable orbits exist and that planets do form in these systems. This means that the potential pool of habitable worlds may be larger than we thought. Binary systems might actually offer interesting possibilities for life. A planet in a circumbinary orbit might experience more stable climates due to the average light from two stars. Or perhaps life could adapt to the complex patterns of light and dark created by multiple suns. Not all planets in binary systems are stable for geological timescales. In some cases, the orbits of planets may be chaotic, with long-term gravitational perturbations from the companion star gradually destabilizing the planetary orbits. Over millions or billions of years, these perturbations could eject planets from the system entirely or send them crashing into one of the stars. This possibility raises interesting questions. Now, how long must a planetary orbit remain stable for life to develop? Could life adapt to a world whose orbit is slowly changing, leading to gradual shifts in climate and seasons over millions of years? These are questions we're only beginning to explore as we discover more exoplanets in binary systems. As you relax and contemplate these ideas, imagine what it would be like to live on a world illuminated by two suns. The patterns of day and night would be complex, perhaps with periods when both stars are up simultaneously, creating a double day of intense light and heat. There might be twilight periods when one sun sets while the other rises, giving you a sunset and sunrise simultaneously on opposite horizons. The night sky would be different too, with one of your suns visible as a bright star, its position slowly changing over years or decades as the binary orbit proceeds. Life on such a world would develop with a different sense of time and rhythm, adapted to the unique patterns created by orbiting within a binary system. As we approach the final portions of our journey, let us turn our thoughts to the future. Binary stars exist on timescales measured in millions and billions of years. What awaits these cosmic partnerships in the eons to come? For most binary systems, the future is gradual change, slow evolution driven by the internal nuclear processes of the stars and their gravitational interactions. Wide binaries will continue their stately orbits, each star evolving at its own pace, perhaps eventually becoming pairs of white dwarfs or other stellar remnants. Close binaries will experience more dramatic transformations, with mass transfer and orbital evolution creating a complex sequence of changes that may last hundreds of millions of years. For binary systems containing massive stars, the future includes supernova explosions, dramatic events that will briefly outshine entire galaxies. When the first massive star explodes, the blast may partially or completely disrupt the binary, ejecting the companion at high velocity or altering the orbit significantly. If the binary survives, it will continue with one normal star and one compact remnant. Later, when the second star also explodes, the system may become a double neutron star or neutron star black hole binary, setting the stage for the final dramatic act in the system's evolution. These exotic binaries are some of the most interesting objects in modern astrophysics. Perhaps the most remarkable future awaiting some binary systems is the merger of compact objects. When two neutron stars, or a neutron star and a black hole orbit each other, they emit gravitational waves, ripples in space-time itself predicted by Einstein's general theory of relativity. These gravitational waves carry energy away from the system, causing the orbit to gradually shrink. Over millions or billions of years, the two objects spiral closer and closer together. Eventually, they merge in a catastrophic collision that releases more energy and gravitational waves than all the stars in the visible universe emit in light during the same time. This is one of the most energetic events that can occur in the cosmos. The merger of two neutron stars is not just a gravitational wave event. It's also an electromagnetic, spectacular. The collision generates a kilonova, a brilliant explosion powered by the rapid radioactive decay of heavy elements forged in the extreme conditions of the merger. For a few days, this kilonova can outshine billions of normal stars. The merger also ejects material rich in heavy elements like gold, platinum, and uranium into space. In fact, many of the heaviest elements in the universe, including much of the gold on Earth, were created in neutron star mergers. These events are cosmic forges, creating matter that cannot be produced any other way. Humanity detected the first gravitational waves from a binary system merger in September of 2015. The signal came from two black holes, each about 30 times the mass of the Sun, that merged together over 1 billion light-years away. Despite the incredible distance, the gravitational waves were strong enough to be detected by the LIGO observatories on Earth, confirming Einstein's century-old prediction and opening a new window on the universe. Since then, dozens of additional mergers have been detected, including mergers of neutron stars. Gravitational wave astronomy has become a powerful new tool for studying binary systems and testing our understanding of gravity under extreme conditions. Looking even farther into the future, we can imagine the ultimate fate of binary systems over truly cosmic timescales. Most binaries will eventually become pairs of stellar remnants, white dwarfs, neutron stars, or black holes orbiting in the darkness. Over trillions of years, even these systems will evolve, though incredibly slowly. Gravitational wave emission will cause the remnants to spiral together, though for most systems this process takes far longer than the current age of the universe. Eventually, in a future almost impossible to comprehend, many binaries will merge, combining into single objects. The universe of the far future will be a darker, quieter place, with the era of stellar companions slowly coming to an end. But this far future is still unimaginably distant. For now and for billions of years to come, binary stars will continue to grace our galaxy and all galaxies with their light and their dances. New binary systems are forming even now in stellar nurseries throughout the universe. Young stars are pairing up, beginning partnerships that will last for cosmic ages. The cycle continues, with birth and evolution and death playing out across billions of individual systems, each unique, each following the same fundamental laws. The story of binary stars is not just a story of the past and present, but an ongoing narrative that will continue as long as stars themselves exist. As you continue to rest and reflect, consider the perspective that binary stars give us on time. These systems operate on timescales far beyond human experience. A single orbital period can span millennia. The evolution from one stage to another takes millions or billions of years. Yet we can understand these processes, model them mathematically, observe them with our instruments. We are brief creatures in a vast cosmos, but our minds can encompass the entire lifetime of stars. This is one of the great gifts of astronomy. It allows us to transcend our immediate experience and comprehend the universe on its own grand terms. Binary stars, in their eternal dances, remind us of both our smallness and our capacity to understand. We've journeyed together through the realm of binary stars, exploring systems ranging from wide visual pairs to contact binaries where stars touch. We've witnessed mass transfer and accretion, supernovae and mergers, planets orbiting double suns. As we prepare to conclude our time together, let us reflect on what these cosmic partnerships mean, both for our understanding of the universe and for our own sense of place within it. Binary stars are not mere curiosities or exceptions. They are the norm, the standard configuration for stars in our galaxy. This realization transforms our picture of the cosmos from a collection of isolated lights to a community of gravitationally bound relationships. There is something almost poetic about the prevalence of binary stars. The universe, at least on stellar scales, seems to prefer partnership over solitude. Stars are born in pairs, live their lives in mutual orbit, and their evolution is shaped by their companions' presence. This suggests that interaction and relationship are fundamental to cosmic structure, not just emergent phenomena, but basic organizing principles of how matter arranges itself under gravity. From the smallest scales of particle physics to the largest scales of galaxy clusters, the universe is relational, with objects existing not in isolation but in networks of mutual influence. For humanity, the study of binary stars has been scientifically invaluable. These systems have given us our best measurements of stellar masses, taught us about stellar evolution, revealed the existence of exotic objects like neutron stars and black holes, and tested our theories of gravity to unprecedented precision. Without binary stars, our understanding of astrophysics would be far more limited. They serve as natural experiments, cosmic laboratories where we can study phenomena impossible to reproduce on Earth. Every time we detect a gravitational wave from a merging binary or observe mass transfer in a close system, we learn something new about how the universe works at its most fundamental level. But beyond the science, there is something deeply satisfying about the aesthetic beauty of binary stars. The image of two stars locked in eternal orbit, each following its elliptical path with mathematical precision, speaks to our sense of order and harmony. The colorful contrasts of stars like Albireo, the dramatic mass transfer in close binaries, the catastrophic power of merging compact objects. These are not just physical phenomena, but cosmic art, nature's own creations of beauty and wonder. When you observe a binary star, you are witnessing one of the universe's most elegant structures, a partnership written in gravity and light. Binary stars also invite us to think about the nature of identity and individuality. When does a binary system stop being two separate stars and become a single merged entity? Contact binaries blur this boundary. Merging compact objects cross it definitively. Yet even in wide binaries, the two stars share a common center of mass, orbit together through the galaxy, and will remain companions for their entire existence. They are separate yet bound, individual yet part of a greater whole. This duality, this coexistence of independence and connection, is a pattern that repeats across many scales and contexts, from atoms to stars to perhaps even aspects of human relationships and society. As our technology advances, we will discover and study binary stars in ever greater detail. Future space telescopes will resolve binary systems in nearby galaxies with unprecedented clarity. Gravitational wave detectors will become more sensitive, hearing the whispers of binary mergers from across the observable universe. We'll discover more exoplanets in binary systems and perhaps someday find evidence of life on a world illuminated by two suns. Each new observation will deepen our understanding and raise new questions. The study of binary stars is not a completed chapter but an ongoing story, one that will continue as long as humans gaze upward and wonder about the lights in the night sky. Before we part, take a moment to simply appreciate the wonder of what we've explored together. Across the vast distances of interstellar space, stars find each other and form partnerships that last for billions of years. They dance to the rhythm of gravity, exchanging mass and energy, influencing each other's evolution in profound ways. Some merge together in spectacular collisions that shake the fabric of space-time. Others remain separate but bound, eternal companions in the cosmic night. These are real physical systems, governed by laws we can write down and understand. Yet they inspire in us a sense of beauty and meaning that transcends the merely physical. As you drift into sleep or continue with your day, carry with you the knowledge that most stars in the galaxy are not alone. They have companions, partners in the great cosmic dance. Perhaps there is something comforting in this, a reminder that even across the vast emptiness of space, connection and relationship persist. The universe pairs up its stars, binding them together with gravity for eons. And we are part of this universe, made of the same matter, following the same laws, capable of comprehending the same beauty. What a remarkable gift that is. Our journey through the realm of binary stars comes to a close, but the stars themselves continue their eternal dances, orbiting, evolving, merging, creating. They have been doing this for billions of years before us and will continue for billions of years after. Thank you for traveling with me through this cosmic landscape of partnerships and companionship. If this exploration has brought you peace or sparked your curiosity, consider subscribing to Cosmic Calm for more journeys into the wonders of the universe. Until next time, look up at the night sky and remember that most of those points of light are not alone. They dance together in the darkness, bound by gravity, partners in the endless cosmic ballet. What will you discover the next time you gaze at the stars?